Michael, thank you.
Sorry?
I was just
Yeah, it's record. It should be recording right now.
I
Okay.
was just going to say thank you for presenting such a new paper. It's very exciting.
Yeah, no worries. Here, okay. Well, let me see, present. Cool, and I can go to like 240 then. Do you guys see the, I guess, slides?
Yeah,
We see the slides
Okay.
with some great DINO animations.
Yeah, let me see.
Those are your images, right? I didn't see those in the paper, I think.
Oh yeah, these are my images or they're from this Tumblr source.
Okay.
But yeah, anyway, we're talking about DINO today, which I guess combines this notion of self-supervised learning with vision transformers to get, I guess, what I'll refer to as like these DINO transformers. Not this, but something else. Anyway, so the paper that I guess this presentation is going to be coming from is this emerging properties in self-supervised vision transformers. As I said, it's pretty new, fresh off archive. And I guess like this crowd doesn't really need a sort of explanation of transformers, but just like quickly, right, for like a review, I mean, we've probably seen this architecture and maybe this looks scary and stuff like that, like, okay, like seems complicated, what's going on? But we're really going to just be sort of dealing with this notion of like, first, like just the encoder, I guess, part, but then also really just like this multi-head attention, this self-attention idea. And I guess like the thing that maybe this is like a hot take, but it's something that like helps me sort of like think about like what exactly transformers are doing with just like all these like self-attention layers like stacked on each other is that I think of it as like a generalized fully connected neural network. And so again, like if we think about sort of like this encoder architecture, right, what's going on here is that at least for just, this is like something from like an NLP tutorial on transformers. The idea, right, is that like, let's say we have like some sequential input, which is like some sentence, right? And each of these are different words. The transformer is nice because we can actually like pass all of these simultaneously instead of like a LSTM or RNN where we process each of these at once. And the idea here, right, is we have this word, we like tokenize it, we get sort of like this embedding as which the transformer can actually like take as an input. And then this thing here, this self-attention sort of like mechanism, I mean, if it looks like a fully connected neural network, it's sort of because I feel like it, at least at some level of abstraction, is like that. The notion is like, yeah, like we have this input, it gets fed through to like the next layer, we get an output. And then so each of these sort of like inputs also has the possibility of taking in sort of like these, I guess, like different representations that are learned, processed through, I guess, like the transformations of sort of like these other sort of inputs, right? And each of these like different like weights is sort of like the attention in a sense. The reason why I'm calling this like a generalized fully connected neural network, and I guess what's like kind of cool is, I guess like, okay, yeah, like when you train this for something like large language, I guess models, right? Like what happens is we mask out one of like the words, and then we look at the output, which is going to be like some like embedding representation. We sort of like train like we have a fully connected sort of network as a head, which gets sort of like the softmax output. And we sort of like say, okay, like, is this like close to what the word actually was? And what's, I guess, cool here is the idea that like ordinarily, right, if we imagine that like this is just like a regular fully connected network, I guess what I'm trying to say is that the, like, yes, when we train the network, right, we're updating the weights, but at the end of the day, right, when we have that trained network, those weights are constant, and we're just feeding in sort of like different images and passing through like the same weights in sort of the neural network to get this output. And then I guess like that output changes depending on sort of like the images that we pass in. But here, what's going on, right, is that because these weights themselves, we think of as like the attention values, are actually changing depending on both like what we're getting in as input and also the output, right? This is like sort of like a more dynamic fully connected network where like the weights themselves actually change depending on sort of like our input and output. And then we also sort of like, we use like that sort of like a newly reconfigured thing to like get the output. And so this is nice, especially for, I guess, like vision applications, because you almost get like those like self-attention like maps for free in the sense of like, yeah, like if I have some image, right? And I'm trying to see, okay, like what are like the, imagine like what are like the, we could pass in like all the pixels in here. We could be like, okay, like what are, given one pixel, right? Like what are the other pixels, I guess, that I'm attending to? And that gives us sort of like these like nice attention maps where ordinarily with like I don't know, if you're training something like ResNet, we have to do some more complicated things to like get like those like visualizations that show, okay, like this network classified the image as like a dog because it was looking at like these pixels. Here we sort of get that for free just through the attention mechanism. And so that's sort of like what's going on here in this pool figure. There's more things here that I'll skip for now, but it's pretty cool. It's like, okay, like, so we sort of like train this network. Again, I'll get into the actual details of like what's actually going on during the training. But imagine that like, yeah, like we could train this network, right, such that like given this image as input, we pass it, and then sort of like we've learned sort of like the attention weights and all that. And then after that, like we can like take like the pixel that corresponds to, or I guess it's a patch actually, a patch that corresponds to something, and we can see, okay, like what are like expect like the attention weights in that like last layer. And so each of those attention weights will correspond to like a different patch. And yeah, like the patches that are sort of like related or more important for, I guess, like this sort of like pixel output will light up as having like higher attention. And so we get like these like very nice things, attention sort of maps, like they segment it really well, but this model wasn't trained at all to do sort of segmentation. It was just trained in like this like self-supervised manner, which I'll get into. Another point that they make is that we get this with DINO, the self-supervised thing. We don't get this with supervised learning of ordinary vision transformers. And maybe if there's time at the end, we can think about like thoughts why. So
Michael, can I ask a quick question?
Yeah.
So on the previous slide, so just to make sure I understand, like you could, the toothbrush bunny image, like you could find potentially the bunny segmentation by masking out a patch of the bunny, right?
Yeah, so I guess like what would happen here, right, is if we, I guess what's going on here, right? Yeah, in order to generate this sort of like a vision attention map, like I think they took like the output of the patch that corresponded to something in the toothbrush and then like just inspect the attention sort of like weights. But if you took like a patch that corresponded to like the bunny, I would imagine like, yeah, like the bunny part would light up in a sense.
And is this just kind of like a fun fact that they don't evaluate quantitatively, I guess? Like, I know the point of this paper wasn't segmentation, so it's kind of a lot to ask for them, like, you know, this is how good the segmentations were, here's where it failed. I'm just curious if they did have any of that sort of discussion.
Yeah, so they actually have a cool result on that, where I have it like at the end, but like as a sneak preview, like if you imagine you just do like some thresholding thing where you say, okay, if this attention map was greater than like some percent, that's part of your segmentation. You can actually get some like nice segmentations out of that. I'm not sure if that was like data set specific, something else to think about. I guess there's a lot of sort of mystery and magic as well, I guess, to the method, at least still for me. And so, yeah, I'm curious, like, I imagine there's lots of hyperparameter tuning, and I'm curious, like, if this type of stuff also works for just like other data sets.
Right. Okay, cool.
Yeah.
Thanks.
So yeah, so what is DINO, right? Actually getting into this, well, I guess like the name itself comes from this notion of self-distillation with no labels. We'll get into that part. And why it's called DINO is because I guess there's a DI in distillation and NO in no, but combine that and you get DINO. It's I guess it's more catchy than like SD and L, but still kind of a stretch. Anyway, but then so we have like DINO, and it actually sort of like takes familiar like components or inspirations from a lot of like the works that I guess we've discussed or referenced in sort of like this 2020 self-supervised learning renaissance, like Bootstrap Your Own Latent, BYO, and SimClear as well, which we discussed before. And then also throws in like this hot new idea of like these vision transformers. So yeah, lots of like fresh things coming together, I guess. And so the authors like make this claim, which I think is actually like pretty motivating, which is that like vision transformers should really shine with unsupervised learning because that's sort of like what a natural or NLP transformer does, right? So if you think about like if you're training like this BERT model, we sort of like had that, I guess, like walk through before, but then again, like the idea here, right? Like, and we're actually trying to train BERT, like what's actually going on is that we have like these sentences. And we mask out one of the things, right? And then we try to like predict like the output. And then yeah, so we get the output, right? And so this is sort of like self-supervised in a sense, right? In the sense that like we have this like task that's just given to us already naturally in our inputs of these, I guess, like sentences. And so they say that, okay, if you can do something like similar to vision transformers, then perhaps like that's where we're going to get like these real benefits, where this like previous like vision transformer paper, yeah, which is here, like did not necessarily do this. And so I guess for a bit of background, just for like the vision transformer, for like why this actually sort of like exists in the first place. I'm not, so admittedly, I'm not super up to date. I don't have all the details on like these ViTs, but my general understanding was that, I don't know, like maybe like you imagine, okay, like it's like you're trying to get like one architecture to rule them all. And so like that's why you would want to sort of like see, okay, like could transformer architectures also work for images? But we have this problem where sort of like this multi-head attention thing, going back to sort of like those things before, if you imagine you're doing like a fully connected thing for all of your different sort of like inputs to outputs, right? This is like hard to, I guess, compute computationally unless you do something like kind of, I guess, like special. Like the, I guess, most obvious thing would just be input all the pixels, treat each pixel as a word and roll out the, I guess, image into like a 256 by 256 sentence. And then I guess feed that into the transformer encoder. But then that's doing like a 256 by 256 by 256 by 256 sort of like quadratic operation each time. And that feels like a lot of work for, I guess, like CFAR10 image that I'm not sure what the equivalent would be for sentences, but I guess sentences are just like a lot easier to work with transformers with. So vision transformers, what they do, I mean, maybe this is not like, this doesn't sound super sort of like novel, but the idea is like you essentially take this image and instead of like feeding in each of these pixels and treating that as like a word, you can take like these patches. And so instead of like 1 by 1, you have like 8 by 8 or 16 by 16. And so each of these is more digestible in the sense that now you only have like one vector each that's like 256. And you get sort of like this embedding. To deal with sort of like the positional stuff, we can leverage the idea of like positional encodings and the natural NLP things. And so what's going on here is that because we're just passing each of these in, right? We don't have like that nice sort of convolutional, I guess, like inductive bias of like nearness. These are just like individual sort of images where I guess, I mean, within the patch maybe, but there's nothing really saying, okay, like, I guess like this is close to this in a sense. And so that's the same thing with like transformers in text where like if you have independent like words, right? I guess LSTMs were nice in the sense that you had this sequential sort of processing of, okay, this word came after this word. Just by itself, sort of like those inputs don't have, I guess, any preposition information when you're feeding them in. So you have this notion of like this like a position embedding that you just like concat into each of these sort of like embeddings. And then the rest of this is still the same as like sort of basically the same as like a NLP transformer. And I guess to emphasize that, right, like the vision transformer itself is like supervised in the sense that to actually get the outputs, or to actually sort of like train this to classify like this image as, this is a pretty bad example I'm just noticing because the classes that they have do not correspond to this at all. But anyway, what's going on here, right, is that like you, instead of like having like taking the output of like one of like these inputs and then sort of like classifying that, what we do is we have this sort of like a extra class embedding, which we pass in. It's sort of like just like this, like, I'm not sure the best way to describe it, but it doesn't correspond to anything in the image. And so we pass this in. And so we treat this though as like a regular like part of the network or a regular part of like the inputs. And then sort of we'll get like this like output here, and this output will have like attention maps from all the other things. And the output can be sort of like thought of as like embedding that we feed into this NLP classifier head, and we get the softmax like that. And so we train all of this, the self-attention, all of that stuff to get like the classify this. Yeah, so I guess back to, I guess, why we want to use DINO. There's this notion of like self-supervised learning with sensible representations. The authors say that, I guess, like in this previous like supervised example, it's not super clear why this would necessarily be like preferable versus like ResNets. But here they say that like, okay, like vision transformers are preferable to convnets when we can do self-supervised learning. And I guess it's also like better. And I guess another claim they make is that like DINO itself, or sorry, yeah. So this table is showing that like, okay, with self-supervised learning with DINO, the vision transformers actually do better than sort of like a ResNet. And I guess to clarify the task here, what they do, sorry, like these rows were spliced together from different parts of the table. But the idea here is that you sort of like pre-train on the images that are in the ImageNet data set without any labels. And then when you evaluate the embeddings, you do sort of like the standard linear thing where you freeze like the architecture and then you put like an NLP on top and you sort of like fine tune that NLP based on like the embeddings and see, okay, like how well you can get on the classification. They also do this interesting K nearest neighbors classification approach. And the idea here is that after you sort of like pre-train on the ImageNet, I guess like images without any labels on your test set, you take an image, you get its embedding, and then you figure out, okay, like what are the nearest, I guess like images, what are the nearest image embeddings that were in my training data? And you figure out, okay, like you find those K nearest ones, and then based on sort of like their classes associated with each of those, you vote for, I guess, like the majority class, and that's your classification. So that's like sort of like zero shot in a sense. And DINO with vision transformers also works better than DINO with ResNets. I think they also compare, I guess, like ResNets with other supervised things, but we'll, I guess, yeah, I'm not entirely sure at the moment. The other thing that they show is that like with vision transformers, this is, I guess, another vision transformer. I'm not exactly sure why it's like what's different about this versus like the ViTs. You get better performance with DINO specifically with these versus these other sort of like, I guess, approaches that you can imagine doing. And so, okay, now we get into sort of like, okay, this is maybe not the best phrase, but like sort of like the method basically of like what DINO is doing. Okay, and so like the idea here, they borrow this idea that we've been sort of like looking with for a while, this augment data with different views. And then this, yeah, very similar to sort of like SimClear in a sense. And then the thing that changes though, I guess what's new about this is like null distillation, like with no labels. That's what makes it DINO again. And so this is like where I guess things change, and it's not super clear to me exactly why each of these individual steps design choices are good. But maybe we can like think about that. But again, back to sort of like the first part, right? Like they do this specific thing called like a multi-crop strategy where instead of sort of just taking like, I guess, views of, or just, they do like a similar sort of like augmentation view thing, right? Where you have like maybe like original source image and you have this augmentation, and they consider sort of like these as like sort of global views. But then you also have, they specifically also sort of like augment for sort of like these different, I guess, like patches, which are considered local views. And the idea here, right, is that if you pass in, I guess, like, let's say this original as like sort of like one thing, and then you sort of like try to like do contrastive learning with respect to like a local view, right? You get like this local to global correspondence where I guess like you're trying to sort of like say, okay, like this image of like a, oh, sorry, what's going on? Sorry, like, so this small image, right, like corresponds, is representing the same core thing as like this large, I guess, image, which I guess is good. And then the second part is this knowledge distillation with self-supervised learning. The main idea here, and try to get into with time, is that we want to train a student network to match the output of a teacher network. And so this is slightly different from the SimClear type stuff, because now each of these individual sort of like networks, they have the same architecture, but they have different weights. They're different actual networks. And the idea here is that, let's say the teacher only gets like these global views, the student gets all the views. And so we're going to be passing in sort of like, for one image, source image, we have these two views. We pass it through sort of like the student and teacher networks, and then we're going to get like these k-dimensional like data representations. And so in the SimClear style stuff, right, we ordinarily do like this, I guess, similarity objective info NCE loss thing to, I guess, supervise the method to say that these two are depicting like the same thing. Instead, what we do is we softmax those representations. And so that's getting sort of like this P1 and P2. And then, yeah, so we get like this distribution over like the dimensions of K. And then what happens after that is we try to minimize like the cross entropy loss of like the softmax distribution of the representation from the student and that of the teacher. And yeah, as I said before, I think it's still not clear to me why this is preferable than like the info and CE stuff.
Quick question here.
Yeah.
What is the centering and the SG?
Okay, yeah, I'll talk about that as well.
Okay.
So SG actually, yeah, right now is, so we only train the student. So so we train this like through SGD, but we don't update the teacher network, teacher parameters through SGD. We only update the student network to match like the output of the teacher network. And so this SG is a stop gradient. Like this is just like a loss or like a dot detach or something in your code that prevents like the gradient from flowing through and updating like the teacher parameters. This centering is, if we go back to, I think I have some, yeah. So if we go back to this, like imagine this is a distribution for, I guess like the student. I forget exactly what centering is trying to do, but I mean, so they do like these two things, centering and sharpening. I think so centering is trying to prevent like the distribution that is output, I guess, like from the teacher network from, I guess, like being too dominated in one dimension. And I'm not entirely sure why. I guess it has something to do with model collapse, which I guess I'll also try to talk about. But centering is a component that essentially tries to make the teacher like a better teacher, such that we can provide like this like supervision for the student to, I guess, like do this cross entropy loss with respect to. But I guess, yeah, I'll try to like think about this through the talk more, and maybe I'll have a better sort of like idea.
I have a few, can I ask a few questions as well?
Yeah.
I also want to suggest, maybe this is a pretty like hefty paper. See, I knew you were signed up for the second half. I wanted to see how people felt about maybe just doing this paper today, and then we can do C's paper in 2 weeks. Does that sound okay? Or would we prefer to still try to fit both in today?
And use the pooling stuff.
Use the polling. I guess it's kind of up to.
Yeah, see you. Like, would that be okay for you or not?
Yeah, sure. I can present the paper 2 weeks later.
Is that okay? Yeah, I apologize for shifting the schedule. I just don't want to rush through this too much and then have you be rushed.
Yeah, I agree.
Okay, so let's do that. Thanks for being flexible. Okay, so then Michael, I have a few questions. So you said the teacher weights are never updated.
Yeah.
Ever? Like they stay random?
I'm going to get into that now with what is the teacher network.
I froze.
Did I?
That shows up for me.
Oh, sorry. I think maybe my connection just flipped out.
For me, that works. Like I have your title. Like, what is the teacher network? I don't know if the others see it too.
Sorry, I froze. I think it was my fault.
Okay.
Yeah. So Sarah, I'm gonna get into this mystery of what is the teacher network.
Okay.
Yeah.
And then I had a few other questions too. If you click back.
Oh, sorry.
Spoiler. Click back to the where you showed the crops and stuff.
Yes, I guess we can do. Let's go back here. Yeah.
Yeah. So okay. So, one question I have is: do they show this only on ImageNet in the paper, or do they do lots of data sets?
They do multiple data sets. I forget if it's lots, but.
And is it always crop and resize to get the local views, or / color distortion, or do they tune those augmentations?
What do you mean by tuning?
Like I know in contrastive learning, which augmentations you choose really impact your performance.
Yeah.
I'm wondering if it's the same here. Like here we have, you do an augmentation to get another global view, and then you do some other augmentations, crop and resize, to get local views. Like, do you have to tune which augmentations you're choosing for each new data set, or do they always use color distortion and crop and resize?
Oh, okay. Yeah, sorry. So they don't only do color distortion. They sort of, I think they employ like the whole host of imaginable augmentations that you could do for just like an image that many of the other self-supervised learning things do. I guess the idea, and this was borrowed from, I think, the MoCo paper, is that we just want to have this dichotomy of, let's say, like these augmentations that are basically depicting the same image, but just like through some augmentation where we see all like the view, like the vision information, but it's just like perhaps like switched in some sense, like color distorted, maybe it's like flipped, maybe you add some Gaussian noise to it, whatever, right? And then you have like this other class of, I guess, augmented views, which are these local views, which are just like cropped parts. And similarly, you can apply the whole host of things you would imagine that would make sense for augmentations to each of the individual sort of like things.
Okay.
Yeah.
There's still probably some dependence, like for each new data set, you probably would still have to play around with different augmentations for what makes sense.
Yeah, I would imagine.
Okay. And then my next question is, if you click forward a few more till there's math. Yeah, there's math. Nice. Okay. So I'm just trying to make sure I have it straight in my head, like all the differences between this and the SimClear paper. So here, obviously, there's two networks. So we're not encouraging the representation out of the same network to be the same.
Mm-hmm.
We're encouraged, and that's kind of probably the primary difference, right? Now we have two networks and we're encouraging the two different networks to have the same representation for the global and local. But otherwise, the loss function looks similar. I don't see what P2 and P1 are.
I see. Yeah. So P2 and P1 should correspond to PT and PS respectively.
Okay.
They are the logits. That's why it's knowledge distillation.
Oh, sorry, Florian, say that one more time.
Yeah, so that's the logits, and that's why it's knowledge distillation. And I assume the teacher network doesn't change. And
yeah, right. So I guess I didn't necessarily get into the knowledge distillation part, right? But it is basically like you want to, given like this teacher network, right? Like usually in knowledge distillation, we imagine this teacher network's like this, like already trained or like this like nice, strong network, right? That like outputs like good things, but it's maybe like too big or something. And so like we want to train like a smaller model to be able to like, I guess like represent everything, the knowledge of the teacher, but in a more distilled sort of package. And so what we can do, right, is supervise the student network to sort of like match the output of, let's say, a teacher network.
I think also in the original paper, one of the messages, it was that they don't try to learn the output classes like after thresholding, but directly like the logit output. So with the, you know, like between 0 and 1 instead of in 0, 1. Yeah.
Mm-hmm.
So
yeah. And so that's sort of like what this like cross entropy loss is, instead of like a 0-1 loss, I guess, trying to capture.
Mm-hmm. Yeah.
Okay, cool.
Makes sense.
Thanks.
Mm-hmm. Yeah. And so, Sarah, that's also like a really good point about, I guess, the distinction between like this versus like the info NCE, or I don't know why, but SimClear, like they call it like the NTXENT. I don't know. It's like the same thing as something before. Anyway, but like it's like very similar. And I think that there's work that precludes SimClear actually that sort of like, I guess like tries to justify why that info NCE loss works, in the sense that it's like sort of like a cross entropy, but you're just trying to like say, okay, like among like my positive and a bunch of negatives, I want to predict the positive as like the right class in a sense, based on like the similarity, treating my similarity as like my, I forget if it's logits or softmax logits that would make sense here, but yeah. But they do this cross entropy thing, and I'm not sure why they do this instead of transformer, I would imagine, or sorry, instead of the SimClear type thing for transformers. Maybe they tried that and it didn't work as well. But it's sort of a mystery to me. And maybe if someone like
the A log B is the mystery part.
Or just like why you do cross entropy, why you do this like softmax, cross entropy of the softmaxes instead of similarity or this info NCE thing of the representations, if that makes sense. But maybe like BYOL actually does. Actually, I'm not sure. I should not talk about stuff.
Do they compare with the same sim clear but on transformers or like vision transformers?
Yeah, they do that. I think, and they show that at least in the main result of doing this on ImageNet that, okay, yeah, that I guess they're better. I think I have that later, but yeah, they show that they're better. Yes.
Do they also show that it helps for the sort of unsupervised segmentation part, or?
Yes, so that's, I think, related to, Sarah asked about this sort of like in respect to this. So, okay, interesting. They don't do this with respect to they don't do this with respect to like self-supervised things, but they compare it against okay, maybe they actually don't do this like in the most comparable way. So I think, okay, I have like a result on the, I guess, like the segmentations from the attention map sort of thing. But I guess, so what they do, right, is that like they train a regular vision transformer to predict with supervised learning to predict the images on ImageNet, and then look at the attention maps and do the segmentation. And they compare that to like if you do like this DINO training method, and they show that the DINO training method, like the segmentations you get out of that are better, like higher Jacquard similarity. Yeah, but we'll get there, I guess, like in a little bit.
Okay.
Yeah. So back to this initial question, I guess, that Sarah had, which was like, what exactly is going on with like this teacher network? And so it's the catch here is that it's sort of like it's the student network in a sense. This is like, it's the exponential moving average of the student network's like parameters. And so what's really going on here, right, is like we first randomly initialize this teacher network, right? And then we randomly initialize both of the networks. But initially this teacher network just outputs sort of like these things that I guess are, I don't know, they're kind of like garbage, I guess, initially. And the student network tries to sort of like match this like thing to the garbage embedding output. But the key thing here is that that garbage was mapped to the same, or like that garbage came from this image, right, of a dog. And so when the student sees like a similar view of the dog, but not the same view, and it tries to like learn some like representation, which in this case is like trying to like, I mean, I'm going to talk about it as like basically like trying to match a similarity of that representation to that output. It's learning that this thing should be, I guess, similar somehow to this other thing that I guess it didn't see, which is kind of weird and trippy to think about. But it's trying to like maybe learn some generalizable thing about this. And it's like supervised in a sense. And so over time, when the student sort of like gets better at doing this matching task, essentially, we're also, by updating based on sort of like gradient descent, we're updating the teacher network basically by copying over some of like the parameters of the student network, and I guess the teacher's current network. And I'll get into like sort of like why this makes sense with this motivation of like model collapse. And so if we go back to, so I guess one key thing here that's probably not necessarily super cognizant or super, cognizant here is that we don't have any concept of negatives yet. And so that's something that like this type of framework avoids. And like other papers like BYOL, also do something similar where you can do like the student teacher training. And by doing this, you avoid having to use sort of like negatives, which can be sort of like a hassle with hard negative mining or sampling lots of negatives for your contrastive learning to, I guess, actually work. And the whole reason behind that sort of thing is this idea of like model collapse. And so if we like think about, go back to SimClear, right? So SimClear, what's going on, right, is that you have the same encoder for both of them. So I guess you could imagine that this is like sort of like, so we have the same encoder architecture that sees both the one image and then it's like alternate view. And it tries to learn some embedding representation that matches, I guess, like the similarity of these two. But one sort of like trivial solution that I guess maximizes agreement, you get like, I guess like max accuracy is like you can cheat by just like learning the same representation for everything. You map everything to like the same like point in representation space, then that's like not good at all with respect to actually learning like these like reasonable representations that encode some information that this is like a dog. But at least based on the subjective alone, right? Like, I mean, you win, you reduce your, I guess, error and get highest, or just you reduce your error. And so that's why you have this idea of like contrast, or that's maybe one idea why you have like this like contrastive setup with negatives, because now what's going on, right, is your objective is not maximally satisfied by just saying, okay, like move everything to like one place. Instead, we have to say, okay, like move these two things that I said are similar to one place. And at the same time, though, you want those two things to be different from this other thing that I said it was different. And so if you're mapping them all to the same place, you don't win anymore. And so now you win if you actually like move them separately. But then as I said, right, like this can require like many negatives. This can require like hard negative mining. I think it is doing some super interesting stuff with like class collisions that could also be troublesome. Yeah, like there's a problem here that I'm not, this is not like super intuitive to me, like the exact challenge, like how hard, I guess, requiring negatives is, but there seems to be like a motivation for self-supervised learning that without sort of like these negative examples. And so I was talking about this a little bit, but maybe this visual will make more sense where if you train two different networks, you can also actually avoid this model collapse solution. And the idea again, right, is that like we imagine we fix one network with these randomly initialized weights, right? And so that's going to output like some dog embedding here, which initially is like garbage and maps somewhere, I guess like kind of random. But then if we train another student network to map this image to a similar spot, right? Then what the student is doing is, I guess it's like trying to, yeah, as I said, like learn to map this sort of like dog thing that it sort of like sees into some embedding spot that this teacher network saw a similar dog thing and chose to map to a spot. And so this initially could be super noisy, right? Like you could have like certain dogs that map to like a certain area and then other dogs that map to a very different area. And that's not great, right? But in the sense of like trying to classify these eventually. But initially what's going on is you're starting at like baby steps. The student is first just trying to say, okay, like when the student gets updated, is trying to basically like learn how to map this similarly to some input that I guess like was similar in a sense. And again, I guess I'm just realizing now as well that the student never actually sees this. And so it's still kind of weird to me why this works, but I guess with some hand waving, we can just say that, okay, like, yeah, like the student is learning like the similarities between this dog and this other dog, which are the same dog. But even if like this embedding output is going somewhere that is not representative or dependent on this core notion of like a dog at all. But if you do this many times and you eventually replace the teacher with that trained student, so now maybe like the student has like some more information, or like a student is better at like mapping similar things, or sorry, the teacher is better at mapping similar things because that's what when it was a student, it was trained to do that. And so now like we can perhaps, if this teacher sees like an image of a dog and sees an image of another dog, then it'll perhaps map them closer to each other, or closer at least than like the garbage randomly initialize the dog embedding. And so we initialize a new student network, and if we keep on doing this, right, we, I guess, similar process, similar stuff. We do this like iteratively over time. We train the student to sort of like learn better sort of like similarity things. And the teacher over time gets better because it is like the student eventually. So yeah, we do this, I guess, iteratively many times. And hopefully that sort of like gives some sense of like why this like exponential moving average thing, I guess, makes sense a little bit, because this is sort of like a not as, I guess, discretized version of like replacing like the teacher with the student and then training a new student, where the student is being updated, but the teacher is also being, the student is being updated, and as the student is being updated, it's like learning is being transferred to the teacher, so that the teacher can like output better embeddings for the student to, I guess, train on.
So does the student get reinitialized to some random thing?
Yeah, so the student actually doesn't get reinitialized to a random thing now in the actual thing. And I guess,
I don't think that would work if you reinitialized. I don't know if this makes sense, but like in a thought experiment, if instead of having a student teacher, you made it symmetric, you made it one was the teacher, the other one was student, and then you alternated and exchanged weights slowly.
Oh yeah, I don't think that makes sense, right? Because
you could do something. They use the exponential weighted approach to do their exchange, but like the way we would do this, if it was like a normal iterative system, is that we would do one and then update the other and go back and forth. And you could kind of imagine doing that with these two networks.
Yeah, so I think that's also something that's like a little bit mysterious to me, but I guess the student doesn't actually get reinitialized every time. I guess what's going on is sort of like the student, I guess even before, right? Like in my sort of toy example, maybe we don't train a new student, we just train the same student. But then the student weights are being updated cumulatively to match sort of like a better representation as like the teacher becomes better. Yeah.
To come back a bit on what Sarah said at the beginning about like how you choose your transformations to create the other image, I think like, I don't know, like intuitively, I would say that in the case of DINO, it's probably even more important, or you choose those for the initial convergence than for SimClear. So if you choose something that is too difficult, it's probably not going to ever converge, right? Whereas in SimClear, I don't know, you could just maybe ignore the difficult cases and you know, still get something from the simpler cases. I don't know, but yeah, it seems like at the beginning, it either will learn something or not. And that's not a given depending on what transformation you have.
I see. Yeah. So I think, yeah, that also makes sense. Like there's sort of like a curriculum learning flavor to that where like, yeah, like if this is just too hard, right, then the student would just never learn something. So you need to start with easier examples and iteratively.
Do they mention that curriculum learning in the paper?
I don't think they do. There are, so it is possible that I skipped this section that related to the data augmentation stuff, but I don't think they do. Let me just quickly double check. No, they do not.
Okay.
But
do you know if anyone has tried a 3D version of one of these augmentations? So where you have a 3D representation that's projected down to 2, because then you could imagine taking the objects and rotating them by a small angle.
Yeah, I think, I mean, that question also applies to like any of the, I guess, recent self-supervised things, right? I'm not sure, are there, do people know if they're like 3D SimClear or things like that out there?
There's, I don't think there's been much. So a major problem is the batch size. A lot of the self-supervised methods rely on having like a really massive batch size in order to get like a ton of those comparisons across. And when you do things in 3D, it just like explodes your GPU space. It gets harder. I think Moco maybe had some stuff in like video, but beyond that, I'm not too sure. I think not in the same settings as like the standard like image ones.
Yeah, I think the way to get around it would be to still do your network is still accepting things in 2D, but you pre-compute your 3D rotations. Like maybe you're using a 3D rendering system, like a game engine or something like that. It's pretty accurate.
Yeah,
generate
or
objects that way.
Oh,
yeah, we had something like we had a presentation like a few weeks ago by Sumik, was doing something that was similar to SimClear, like on 3D brain images, you know, like trying to detect some vessels. And what he's doing, I think, is just like you know, taking like patches, 3D patches, and then you can solve this problem somehow. So it depends like how big your object is, you know, like let's say if he wants to detect the vessels, it doesn't need to have like the full image view. So that's okay to take patches, but if you want to take if you need to see the full image to be able to make your predictions, then that's a problem.
Yeah, that's curious. Well, let me see. Okay, yeah. So I guess I'll probably try to skip to results now. There is like this mystery of, I guess, why the cross entropy that I brought up before. There's something to do with like the centering and sharpening thing, which is also, I guess, there to prevent sort of model collapse. But these are things that we can defer for later. We want to get to some interesting things. So I guess these are not actually like super interesting results right now. These just show, okay, on their main evaluation task, which is, okay, can we learn good embeddings from an image set, data set that without labels, and then evaluate those, I guess, learned embeddings on this fine tuning task with labels, or the zero shot classification thing. They show that across sort of like architecture, or keeping architecture constant across sort of like these like training methods. DINO seems to be the best out of like these comparable self-supervised learning things. And then same with different architectures. So keeping sort of like the vision transformer architecture, I guess like the same, compare against these. And then finally, I guess with respect to comparison across architectures, and I guess this is like a little bit, I'm not super clear how to parse this one, but DINO, I guess, does best for all the things that you can compare it to. And so I guess another interesting thing here is that it also works for sort of like a transfer learning, where instead of sort of evaluating on, I guess, test data that came from the same data source as ImageNet, or as your training data, so ImageNet, we can do this on sort of like these new sort of like test sets presented to us. And in this case, we actually do, I mean, we do better than sort of supervised learning, which perhaps suggests that, like, again, like it feeds the narrative of self-supervised embeddings being preferable, or learning some better information or transferability than supervised things, which might be sort of constrained in some sense. But then they also do like these downstream tasks with vision transformers. And so here, it's not super clear to me why necessarily these would be preferable with like vision transformers as opposed to like other architectures like ResNets. But there's this idea of like image retrieval, which is, okay, like after you've trained on some arbitrary collection of images, in their case, ImageNet, or this like Google Landmarks data set, can we learn embeddings such that, like, okay, like now if I'm given like a new data set, Oxford or Paris, like these Oxford or Paris place data sets, if I feed in like a test image into my, like, can I, or sort of like, does my model sort of like learn embeddings that sort of like map, like, I guess, the similarities of like these images that would make sense? This other idea of like copy detection is also sort of like similar to this. Okay, like, is our model essentially learning like a similarity, some notion of like similarity with respect to images that it has never seen before, which is, okay, like, can you recognize pairs of image where one is like a distortion of the other? So that's kind of interesting. So something that's like perhaps like more provocative and cool about like the self-supervised transformers thing again is that it goes back to this idea of like the attention maps. And so again, like through the training of the transformers, right, we sort of like get like this notion of, I guess, the initial thing, like the beginning, this stuff was like the saliency maps and things like that. But now we have like this idea of like, we can do this like automatically just through looking at like the last layer, like the attention maps corresponding to each of the different outputs. And so the transformer actually has like multiple heads, and what they say is that, okay, like different heads correspond to attending to different parts of the image, which is pretty interesting. And I don't really have like a good intuition of like what's going on there. But another thing, like this sort of like shows like, yeah, like pretty clear. This shows like, I guess like how they actually generated like those like vision, or sorry, the attention maps from before, right? Which is like, okay, like after you've trained your model, when you feed sort of like this image into the vision transformer, right? And you sort of like look at like the output of the transformer that corresponded to the patch here, and you look at all the attention maps, then you get, I guess, like for any of those specific sort of like patches, you can see like, okay, like what are like the other sort of like patches that light up were attended to. So yeah, like that's pretty cool. And they show that this is actually better here than versus if you try to train the vision transformer with like a supervised approach, which is, I guess, here. Yeah. So the attention maps that you can actually generate are, they actually seem to work at sort of like the segmentation thing for the, if you do this in a self-supervised manner with DINO. But if you try to just train this vision transformer in a supervised approach, right, you don't actually get this, which is kind of weird, or maybe you somewhat do with like this like last part here. And I think like the intuition here, right, is that if you can imagine, go back to sort of like what the actual vision transformer is trying to do in a supervised manner, you have that image, you flatten it essentially, and you pass it through the transformer, but at the end of the day, you're still trying to only predict, let's say, this single output. And so it could be the case that like this objective of the output just being like one class loses a lot of information, where here, when what we're doing with like sort of like these different views, yeah, like these different views, like perhaps like you're also incorporating more of like that, like those like pretext tasks that you sort of like see in like natural like mass language modeling, where you're trying to predict something based on like other sort of like I guess like the surrounding text in a sense. I'm not sure if that was a super clear sort of like explanation. I think this is also still a little bit mysterious to me, but it's pretty interesting. And so just as like sorry?
A question on that?
Yeah.
So could it also be that the supervised model just overfit? Like, did they have some pre-training, any sort of pre-training, or not? The one on the right here.
Yeah, I don't think they do. I think this is just like, okay, like if you take vision transformer and ImageNet and you train with DINO versus train the vision transformer with ImageNet in a supervised manner, assuming you have the labels. This is your behavior of the attention maps.
Okay. Okay.
Did they show comparison to other self-supervised?
Yeah, they don't, which I think would be cool.